Yulin, are you there?
Hi, yeah.
Okay, can you share your
Okay,
PowerPoint?
let me try.
Yeah.
Okay.
Okay.
Can you see the screen?
Yes, yes.
Okay, let me try. I think I need to swap it, right? How
Okay.
does it look now?
Yeah, it looks perfect. So
Okay.
the next speaker will be Yulin Chen, Professor Yulin Chen from Oxford University, and he will be talking about exploring topological electronic structures in quasi-1D materials. Please go ahead.
Okay, thanks, Huang, for the introduction, and thanks the organizer for the invitation. I think I was supposed to give a talk in RISE a couple of years ago, but due to the COVID and other things, and that never happened. I'm really glad that today I got the opportunity to do this. Although with the time past, the topics has changed. Now it's about the quasi-one-dimensional topological quantum materials. And to be honest, our group work is focused on the 2D and 3D, but recently we did try to explore the topological electronic structures in quasi-1D materials. Since now the time is relatively abundant, so I would like to introduce a few of our recent works along this path. I think in this audience, there's no need for me to do the introduction about the progress of the topological materials, starting from the quantum Hall effect, and then more recently quantum spin Hall effect, then the 2D and 3D topological insulator, topological crystalline insulator, and topological direct wire sand metal, and eventually recently then people start to attack the topological superconductors. And I don't think I need to talk about the fuss of the topological superconductors, because it can be used, well, it can host this exotic Majorana fermion, and it can be used as a quantum qubit material for the quantum topological quantum computation. Well, yeah, then there are basically two broad route to realize the topological superconductors. One is to make heterostructures, and then man-made structures. For example, you have a superconductor substrate, and then you put on the topological material on top of it, and then apply the magnetic layer or the gating layer to control all this and to make a device out of it. That's pretty nice. And there's also another route, is that the search for the intrinsic three-dimensional topological superconductor candidates. And I think people are exploring both routes. And in the past few years, the first route has been carried out very extensively. A lot of groups have been doing this. For example, like you just grow a layer of topological insulators on the conventional superconductors, and like the bismuth selenide on the niobium selenide. I think this one. And then also people also fabricated more sophisticated device, try to realize and observe the characteristic signal from the Majorana fermion. But unfortunately, this route turned out to be quite difficult. And then, for example, one of this work was recently retracted, and this was the 2D films. And then there's also a 1D system that people try to do the nanowire and couple it with superconductors. And also this route recently encounters some difficulty too. Then it shows that although it's promising, and then there are a lot of details in the device fabrication and the measurement that people need to be very careful about. And so this not necessarily a bad thing, this the retraction and expression of concern. This just means this is difficult subject, and then we should motivate and get people in the field and also get more resource in doing this. And for my group, then, because we are not expert in dealing with the material growth or the transport measurement, so we actually took the second route. We are trying to search for three-dimensional topological superconductor candidates. And then by exploring the electronic structure and then look for the signatures of the topological superconductor. And there are already a few unconventional or topological superconductor candidates, the bulk materials, for example, like strontium luthenate. Of course, there are also some new discoveries about the measurement of this material, and then we'll wait and see what's the real physics in there. And also there are other such as a copper-doped bismuth selenide, palladium-doped bismuth telluride, and also more recently the iron tellurium selenium system that people realize they could be the topological superconductor candidates. Right. But many of these materials have some defect. Well, there's some shortcomings. For example, like a lot of these materials are doped, so they are not stoichiometric, and so they sometimes is unstable, like a copper-doped bismuth selenide, and so they may not be very device friendly. So for us, we'll then try to look for the materials that is stable and it's stoichiometric, and then it's more device friendly. By meaning device friendly means that you can either grow them easily, or you can just exfoliate them and just manipulate them. And there are a lot of these other bulk candidates proposed. For example, like the whole families of half-Heusler compounds. There's a phase diagram. You can see that below this, the zero line, then all these materials are topological. And then if they are superconductor, they could be topological superconductor candidates. But in this workshop, then there's so many of them. But in this workshop, we focus on the quasi-one-dimensional materials. Then I will start from the recent candidate we study, which is a quasi-one-dimensional material, which is tantalum triselenide. So when we try to study low-dimensional materials using ARPES method, in addition to the regular ARPES, then we sometimes use a micro and nano ARPES measurement. I think Professor Kondo yesterday shows such measurement. And then by doing the micro and nano ARPES, we can focus the beam spot to a very small area, and then therefore can study the small structures. For example, like the nano wire, ribbon, plates, then we study all these things. But if we want to really study one single nanotube or a step edge, this could still be difficult, because even for the most advanced nano ARPES facility, and then the beam spot is about only a little bit more than 100 nanometers. So compared to the size of the width of a nano ribbon or nano wire is still pretty big. So we still hope that we can get this quasi-one-dimensional material to crystalline into 2D or 3D form, so that we can use the micro or regular ARPES to study them. Basically, we just have all this nanostructure and then 1D structure aligned or in perfect order, so we can study them. And then the first example I want to share is the tantalum triselenide. The tantalum triselenide has been shown to be possible superconductors a long time ago. And you can see from this transport measurement, and there's a sudden resistance drop around 1.25 Kelvin. Of course, it doesn't reach zero, and then we think that's possibly there's a defect in the material, and so that the superconducting volume is not large enough. And more recently, according to the band structure calculation and analysis, and this material could be topological, and then there's a selenium p orbital and tantalum and d orbital can reverse their order. So with this motivation, then we want to take a look at the band structure of this material. And you can see that the crystal structure of tantalum triselenide is formed by the two types of tantalum triselenide 1D train. And this is along the B direction, and you can see that the crystal we grow is indeed formed by the very tiny fibers of this, and resemble to this the tantalum triselenide wires, and they loosely form the quasi-2-dimensional, three-dimensional crystal, and then they can easily be cleaved. And on the right here hand side, I show the cleave plane. So a lot of this the tantalum triselenide, the chains and just organize themselves like the packed chocolate bars, right? Then the exposed of atomically flat surface. However, it is quasi-1-dimensional. The cleave plane is pretty rough. So that's why we need to use the micro ARPES, so take advantage of the small beam spots, so that we can get the relatively flat surface of this material. So, and then on our sample, our transport characterization and confirm the previous observation, and then even better that we can increase the onset of the TC, and then with a quote TC, this from 1.25 Kelvin from the literature to 1.75 around there by half Kelvin. And then the quantum oscillation also show clear periodicities, show the high quality of the material. And then we had to confirm is a quasi-1-dimensional structure. We also use the STM measurement. And then this is show the 1D the tantalum triselenide trains. And then you can see clearly the superconducting gap happens when the temperature drop below the transition, which is around 1.75 Kelvin. And then you can see the gap opening. And then very interestingly, even if we vary the STS, the tip, STM tip position across the wire, and then you can see in this inset here, from the line 1 to one of this chain to the other, and then we just sample 6 points, and then we measure this STS spectra, and then they show quite similar behavior, and then it's homogeneous on the surface. That's very good for our ARPES measurement. Otherwise, then because ARPES measurement doesn't have the resolution of the STM, so typically in this measurement we have only 10 micron resolution. So if the material property is inhomogeneous on the surface, then ARPES can only measure the average signal. But in this case, we're assured that the surface is pretty homogeneous. So then we just take a ARPES measurement on this sample, and you can see, and we first did this DFT calculation, and which show there are 3 Fermi surface pocket in the bulk brilliant zone, and then if we cut through here, and we can see this quasi-1D behavior is pretty clear, and then you can see the horizontal line. Of course, it's quasi-1D, it's not exact 1D. So we can see there's one pocket at a alpha, which are X point, and then one pocket as a gamma point. So this is consistent with the quantum oscillation result that show the 2 periodicity that correspond to the 2 bulk pockets. But then in addition to these bulk pockets, we also see something definitely we see more than 2 Fermi surface pocket. Then what are those? Then our guess was that these are the surface state. So, and indeed, if we do the calculation, and we were able to find, and then if you can see my cursor here, and then the calculation show this the broken red line is this topological surface state from our calculation, and then that was discernible from our measurement, and you can see it's also from this dispersion, and also from this constant energy contour plot. So this topological surface state pocket and the 2 bulk state pocket make up the complicated quasi-1D Fermi surface of this material. And then if we zoom in to the X pocket where our calculations show the inversion happens, band inversion happens. And we can see, okay, in general, it looks pretty similar to the calculation. And then there's the W shape, the conduction band pocket here. And then you can see there are a reminiscence of the two pocket here. And then the Fermi surface may not be exactly the same as in the calculation. And then also the bulk pocket is, the conduction of a valence pocket is below. But then if we want to see the topological surface state here, then we need to zoom in a little bit. But the thing is that because the energy scale is too small, then the typical synchrotron ARPES measurement doesn't really have the resolution to tell if there is any the topological surface state inside this gap between the bulk conduction band and the bulk valence band. Rather, we only saw a bunch of blurry bands. Right? Even if we do the second derivative, we were not very sure whether there's indeed a topological surface. Of course, it looks similar to the calculation, but we do need to have a more clearer experiment results. So that's why we turn to do the measurement under using the laser light source. The laser light source has the advantage of a very small beam spot that we can control, and also it has a very high energy resolution, and also because it's low energy, then it also has a very high momentum resolution compared to the synchrotron ARPES measurement. And then if we just zoom into that region we just saw before here, and then we were able to see that now in addition to the blurry bulk conduction and the valence band, there are definitely something in the middle. And then you can see clearly if we take a derivative of the spectra, and also you can see in this different cutting direction, the gamma to X to gamma, you can see definitely there's something in here, and the red broken lines are just the guide of the eye. Okay, so there are surface state live inside the bulk gap of the conduction and valence band of the tantalum trisulfide, and then so that we confirm that this material does have a topological electronic structure in it. Of course, then because the temperature, the superconducting temperature of this material is so low, it's 1.75 Kelvin. So then the current our ARPES spectrometer cannot go down below that. So we were not able to tell whether the topological surface state got gapped. So that's why we claim this material as the topological superconductor candidate. And then then we encourage the transport colleagues and to study this, because the transport temperature can go well below this. It's a superconducting transition temperature, and then this is quasi-1-dimensional material and easy to be exfoliated and separated, and I can make device out of it. But
Yulin, can I
yes.
ask a question?
Sure.
So what make this tantalum sulfide unique? Because this structure, actually there are many other materials having the similar structure as this.
Oh, I think in terms of the superconductivity, that's I think that's a separate superconductivity and topological property. They are separate, right? Then, so I assume that you ask why this thing is topological.
So, yeah, I believe topological perspective might be important, because in terms of superconductivity, because you just mentioned that this particular one, TC is very low, right?
Yeah.
One of the materials I have been working on before a while back is actually a zirconium telluride 3. I believe they are the same structure.
I think that's similar.
That TC is higher, I think around 4.5. It should be reachable for your guys, some of your guys.
Unfortunately, 4.5 now is still difficult, but we're working on that. Hopefully, in a year or two, we will have the instrument to deal with
But the similar other ones might have even higher one. Okay, I think
yes.
I have some impression. Some of them might be even higher. And
right.
If I remember correctly, tantalum triselenide also have a charge density wave. That is also having charge density wave as well. Right?
Yeah, so a lot of this Quasi-1D material has CDW. But so
right?
yeah.
So in this way, the uniqueness for this one is because of the topological aspect, you think? I don't know zirconium telluride 3 because telluride is there. Spin orbital coupling has to be strong too, right? I don't know whether they are topological or not. Okay, that's something I probably have to look into.
We also study similar other materials like zirconium and hafnium, tellurium, and seleniums. And the reason I didn't show is pretty obvious that the result was not as good as this one.
Okay,
it may be the sample issue, it may be our cleave problem, or it was just the unlucky that then our measurement the condition for those materials not ideal at that time. But I will talk about more of the similar materials next.
Okay, yeah. Thank you.
Thanks. So for this one, and although we saw the signature of the topological electronic structure, it's not ideal, and then we still don't see the in the superconducting state, and then we don't see the gap opening. So then we move on to another one. So this is another topological superconductor candidate is a 2M phase tantalum disulfide. Oh, I forgot to mention this work is done by Chen. Our Oxford graduate now is a postdoc and then stationed at ALS. And then the second work is done by also an Oxford graduate, and that's Yiwei, and he's now the faculty member of the Wuhan University. And then we chose this material is because then it has the highest TC among all the transition dichalcogenide in the natural form. It's up to 8.8 Kelvin. Then we can reach it at this stage. So in this material, and it's also pretty friendly to us. It's a layered material, so it's friendly to ARPES. We can get atomically clean surface. Although this 2M phase is not very stable in the air, so we just need to prepare and measure very quickly, and then preserve. It's almost impossible to keep the sample for longer than a few months. But the structure itself is pretty nice. And according to our band structure analysis, there are also band inversion happening. And so we expect that at the gamma point, there should be the topological surface state. And because of the transition temperature is pretty high, 8.8 Kelvin, so we hope that we can see the gap, superconducting gap opening at the topological surface state, as well as the bulk state. So, and then here is the basic characterization of the sample. And then our STM measurements show a very nice surface, and then formed by the sulfur chain on the surface, and without the reconstruction. Yeah, a lot of those transition trichogenides, and then have the CDW or other all the surface reconstruction, but luckily this material doesn't have that. So, and then the bulk structural the measurements show that the phase is correct. So then we just carry on the ARPES measurement on this material, and you can see then the band structure is quite one-dimensional, because you can see that the Fermi surface is quasi-1D, and then of course plus some 2D pockets here, because it's more two-dimensional than the previous candidate is a tantalum triselenide. And in here, then I think I don't need to go into the details of the bulk structure, other than saying that then it's quite ARPES friendly, and our measurement is of high quality, and then we can compare the result to the calculation 1-to-1, and they show very overall agreement, right? And then both in the constant energy map and as well as the band dispersions. And this gives us confidence that if we see something different from the bulk states, then it should be surface, and then it can, and also our calculations should be reliable. And according to our calculation, that at the gamma point in between the conduction bulk conduction and valence band, there's a M shape, the topological surface state inside this tiny gap. This is still difficult to see because if you notice that the scale, this is only less than 0.1 inverse angstrom. So then in this case, we also turn to the laser ARPES so that we can have a higher momentum resolution as well as energy resolution. So at the beginning, you can see in this area, if you can see my cursor, on the left-hand side is experiment, on the right-hand side is experiment overlapped with a calculation. And you can see clearly that in addition to the bulk band with pretty broad bulk band, we see there's a pretty sharp dispersion here, which should be the topological surface state. But unfortunately, at the S-grown sample, and the Fermi surface is lower than the neutral one, so we can see high, and then the Fermi surface is lower than a Dirac point. So in addition, in order to see this Dirac point, and then we carry on some trick, and then which is typically used by the ARPES guys, then we just dope some potassium on top of it. So the potassium will donate some of the electrons and lift the Fermi level. And then indeed, you see that after this doping, and then the whole band just sink a little bit. And then we can see this, the crossing of the topological surface state and also the Dirac point. And then on the right-hand side, on the top row, you can see the comparison between the pristine sample and the potassium doped sample. And the Fermi surface was actually lifted by about 45 millieV. Then we can see the whole branch of this topological surface state. Now, this gives us confidence that this material is topologically non-trivial. And in addition to this evidence of the dispersion, and we can also see from the constant energy contour, you can see that the constant energy contour, in addition to the bulk states Fermi surface pockets, right? You can see clearly there are additional features that is definitely not the bulk state. This agree well with the calculation of the topological surface state Fermi surface. So this also confirmed that the topological surface state exists in this material. So the next step is to see whether we can go into the superconducting state and check if the surface state also got the superconducting gap. So, and for this sample, luckily then the TC is relatively high. We were able to get to 6 Kelvin sample temperature nowadays. And you can see that the temperature dependent measurement and the 6 Kelvin, there's an overall gapped spectra. This is the symmetrized the ARPES spectral map. So you can see that there's a gap around the zero energy, which is a Fermi energy. On the other hand, if we merely increase the temperature by less than 5 Kelvin, and this gap disappear. And we can see that here we have both the bulk states and the surface state dispersion. Both of them were gapped under the superconducting transition temperature. And you can see this transition more clearly from the momentum distribution curve on the right-hand side. The 10.8 K, there's no gap, and then you just, when we decrease the temperature, the gap start to show and then get more and more prominent at 6 Kelvin. And here, and then we just separate out the dispersion of the topological surface state and the bulk state. And you can see clearly how this gap closed upon the temperature rising. And then if we just extract the data from this measurement and then we plot together, and you can see this starting from around, well, 8.8 or 9 Kelvin, then the gap start opening. And then interestingly, and then the gap magnitude of the topological surface state and the bulk state, they are very similar. So this leads us to think that this the surface state bulk gap comes from the proximity effect from the bulk, and that I think makes sense. So here, and then in addition to the magnitude of the gap, we also study the anisotropy of the gap. So because the ARPES, we can measure different momentum, so we can measure the gap magnitude versus the angle, the in-plane angle. And then we plot this gap magnitude. On the right-hand side, you can see that this gap magnitude doesn't really vary with its direction in the momentum space. And then also you can see from the bottom left panel, and this look like a homogeneous gap without the node. So, and then from the fact that the gap of the surface state and the bulk state opens relatively at relatively the same temperature and also reach the similar magnitude, then we conclude that this topological surface state is gapped by the proximity effect from the bulk superconductivity, and this will lead to the possible of the formation of a Majorana mode on the surface if we just apply the magnetic field on it. I think so far this is the clearest the gap opening below TC that we can and we can see in any topological superconductor candidates. And also this material is relatively stable and it's stoichiometric. So we hope that the colleagues in transport, you guys can find use of it.
Yulin, may I raise a question here?
Yeah, sure.
Yeah, the data is really impressive. So my question is really simple. So what is the energy resolution of your ARPES measurement for the superconducting gap?
Oh, the gap is about 2 millieV. The resolution you can see from here, and our spectra. I should have put a raw spectra here, but you can see from this one. Can you see my cursor?
Yes. So,
and then you can see the quasi particle peak drop, right? 0, and then with one small tick is 2.5 millieV. So and then the resolution is smaller than that because you can see the full drop of the spectrum. So we actually did the gold measurement that was about 1. I think it's slightly less than 2, is a 1.5, between 1.5 to 2. I need to double check, but it's around that range. And the reason we cannot go lower is that there are a few reasons. One is that the temperature is still not very low, and also the laser. And then even though this our laser is the quasi continuous laser, and then the resolution is still around one millieV, and coupled with this temperature, and then also there's also some surface variation. So yeah, that contribute to the overall 1.5 to 2 Kelvin to 2 millieV's resolution. So if we want to study the material with lower superconducting temperature, then we need to decrease the cryostat temperature. We also need to improve the instrument temperature, the resolution. Oh, also this resolution also is also affected by the analyzer itself. So the analyzer now we use the Sienta DA30, so the resolution is less than 2, but yeah. So I think that also limit the resolution we can get.
Okay, thanks.
So okay, that conclude the superconducting part of the talk of my talk. So here then I saw that the topics of the workshop is a design material, right, and to engineer the material. So I think I I'll put a couple of examples in this talk to show how we can vary the system and study the material with controlled parameters. So here's a tunable. Yeah.
Sorry, a reminder, 5 minutes left.
Oh, 5 minutes. Okay, that's fine. So then the last one is quick. So we have a tunable 1D direct lines in niobium silicon tellurium 1, 2. Basically, the concept is pretty straightforward. We have this. You can see that this material is made up of this the building block niobium silicon tellurium and niobium tellurium 2. So niobium tellurium 2 layer, the train is conductive, and the other one is not. So we basically will just want to vary this n, and then so to adding more insulating layer between the conductive niobium tellurium 2, so that and then when the n increase, then the conducting layers are the chains are further aparted, so there is more one-dimensional, otherwise it's more two-dimensional. And then I just go to the comparison paragraph, the slide, and you can see that for the further apart the conducting layer line, the chains, you can see that the one-dimensionality is better. So, and then if we just move them closer so they can interact, you can see that they are more two-dimensional. Right. So basically this one way, and of course we can vary this X or make this the trains between the two conducting layers more and more, then it can be more and more ideally 1D trains compounds. Okay, so and then the last one is that the most recent try of us into the one-dimensional system. So I think in this audience, I don't need to talk about this dimension crossover. Basically, and then in one-dimensional, people talk about the non-Fermi liquid behavior, and then it's a Luttinger liquid. And so different from the Fermi liquid and Luttinger liquid, and obey this you can scale it, right? This the exponential law. So have this coefficient. And so, and then this works mainly did by the Chen and the Tsinghua University. And so, and then, for example, like a typical Luttinger liquid compound, and it's formed by this alkali, the moly oxide. So it have formed these trains, and then this is well known for a long time. So we're not going into details. Okay, we can just scale it and then put all the spectra together. So this is pretty typical Luttinger liquid behavior. But interestingly, recently we found this two-dimensional material, this eta phase of the moly oxide, and it doesn't have an obvious one-dimensional train. And then, for example, like the Lawi show the high quality of the material, and then also show the two-dimensionality of the material. And surprisingly, they also show the Luttinger liquid behavior. So, and then we were wondering why this would happen, because it is clearly, you can see from the structure here, right? This 2D plane. So it turns out, and then you can see the Fermi surface map. You can see that there are three parallel groups of parallel lines represent the three train directions, and then in between this linear surface Fermi surfaces, and then there are anti-crossing behavior showing there's 1D trains, they have interaction. So how can we find this 1D train in this apparently two-dimensional surface? So, and then it turns out that it is the different orbital of the atoms that give us this hidden 1D train. Then we call it orbital trains, and there are three groups of them. And these three groups, they cross each other, and interestingly, then they have weak interaction between them. This realized the cross-Luttinger liquid model that was proposed by Charlie Ken and his collaborators about 20 years ago. So this is very interesting, the model system that may generalize the large liquid behavior into a higher dimensional and may be used to explain some strongly correlated phenomena in high dimensional materials. So then the next thing we would like to do is certainly to explore whether there are some topological properties in this kind of large liquid trains. Okay, so in the last, I think I will skip that if anyone is interested, and then you can ask. So because I learned that in RISE, you're trying to make this the vacuum interconnected system. That's what we have been doing, because to study the low dimensional materials, then a lot of them is environment sensitive. We need to keep it in the ultra high vacuum. So we make a suite of the characterization tool to use the ARPES and other related technique. They are connected by the vacuum highways, and like you can grow the sample, and then you can measure the STM or ARPES or even the transport. So, and then that's the version 1. And then version 2 we have is for built in the laboratory of topological physics. And that was the 2018, the design. And then after 4 years hard work, then now it's in shape. And then we are doing the final characterization and test. And hopefully very soon, then we can make use of this. And then we certainly very welcome the collaborators and the audience from the audience. And then the questions, whether we can go to lower temperature, and in this system, yes, we plan to go down to 1.5 Kelvin, and then the energy resolution is go below 1 millieV, and then also for the STM and inline in situ transport, then hopefully we already got the dilution fridge, and then hopefully can go down to less than 50 Kelvin, millikelvin to 10 millikelvin regime. Okay, with that, I thank you for your attention. Thank you.
Okay, thank you, Yulin, very much. Let's open for a question. Yeah, so I have a question on the Ledinger liquid topic. You showed the cross Ledinger liquid picture. So can you say a little bit more about the structure of this crossing? Like it's not a square lattice, right? If you just draw these 3 arrays of
let me see whether I have this in my backup slides. Yeah, here it looks probably you have a better view. So it's actually made up of this the moly oxide octahedrons, and then they are not 90 degrees apart, and then you can see it formed a 2-dimensional network, but you can still separate them. For example, like this is the train along B direction here, and then the train along the B and B plus C direction here. But if you see the structure, it's really difficult. Yeah, then you may ask why you want to separate this chain along this specific direction, right? I can still do other directions. But then if you take a look at the orbital character, you can see that. And this, the orbitals of the atoms, they form only 3 like highway, like trains. And then dxy, dyz, and dxz. So these 3 trains are conductive. And they share, actually, they share the octahedra, and then they cross only at some point, and then at this crossing point they have some interaction. So this is pretty neat, because before this the crossed large liquid model was only be attained by putting the carbon nanotube together, right? But that requires a lot of effort, and it doesn't form a uniform large crystal that we can study.
So what's the temperature? Yeah, sorry. So what's the temperature you have for this material?
You mean the measurement temperature, or?
Yes. Well, you know, when you measure this material.
When we measure this, is actually the large liquid behavior. I think we were able to see from a broad temperature range. Let me see. See, we actually do the temperature, vary temperature from 20 Kelvin to 135 Kelvin. So pretty broad range. They all show this behavior.
I see. That's very interesting. So I'm wondering if any transport experiments can be done on this as well.
Definitely, we encourage you guys to do that. Then I think for the other the moly oxide system, then a lot of transport has been done. For example, like this one, and then the literature go back to about 16 years ago. But for this material, there's some literature, but not many of them.
Okay, thank you.
May I have a following question? So the reason those orbitals are responsible for the cross the larger liquid behavior, is that because you check the Fermi surface in the band structure?
The
band.
Yeah. So yeah, we were quite surprised at the beginning, right? So and then we checked the Fermi surface, and we were then we understand that there should exist 3 different chains, right? They have different directions. There are 3 sets, about 60 degrees apart, but not exactly. And so, and then we carry out the calculation, and the calculations show there are 3. This the direction is the special, and then this more conductive, and then the orbital can form. They have more overlap, just along this 3 direction. Therefore, forms 3 sets of chains, and then this 3 sets of chains, and then actually, if we just analyze the angle and also do the calculation, that the result agree with our measurement very well. You can see on the right-hand side is our calculation.
So particularly there's no threefold rotational symmetry. It's just a rough,
No,
symmetry, right?
yeah, it's not
even in the calculation, I guess.
Yeah, even in the calculation, it's not. You can see here, it's not threefold, right? It's it's not exactly 60 degrees.
Right.
It's deformed a little bit. Yeah.
Okay, thanks.
Yeah, thank you.
Okay, I think perhaps we should move to the next talk, and let's thank Yulin again.
All right, thank you.
Okay, so the next speaker will be Ginny Lau from Ohio State University. Ginny, are you there?
Yes, I'm here. Let's see. I need.
Yeah. Can you share the screen?
Okay.